Okay, so we talked about different forms of logic and different forms of logic expressions. To expand on this a little bit, we have to talk about set notation. It's talking about all the different elements that go into a set. We've already talked about set notation, and we've also talked about Venn diagrams before, so I think this section shouldn't be too hard. It's not super complicated. The hard part, I think, is just dealing with the notation and all of the ways that we can express it. But in general, to talk about a set, it's really looking at all the different elements that are involved in some certain thing. So a lot of times we talk about sets and like probability, the amount of options that we have. So for example, if I flip a coin, it's either heads or tails. So the whole set that it could be would be either heads or tails, or two elements that are in that set of options or outcomes. But that's not the only time that we use different sets. We use sets in lots of different ways, but it really just is a collection of different elements or different outcomes or however you want to say it. So to express the idea that we're using a set, we use these curly brackets, and then we list all the elements that go inside. It is important, by the way, that we're using curly brackets. You could just do like this if you want to, that's fine. But the important of dealing with a set specifically is that there's no order. So when we use parentheses like this, that's indicating an order, like x comma y. It's an ordered pair. It matters that this is 1 and 2. This is not the same thing as 2, 1. We know that, right? Because that's a different point in space. So this is since we're dealing with parentheses here, it's in order. Set notation, if I deal with a set of 1 and 2, this is exactly the same thing as 2 comma 1. So in these curly brackets, the order does not matter at all. So it's important that we do surround our elements with not parentheses, but we use our curly brackets, our set notation. Sets can have numbers, it can have variables, objects, edges, etc. Like you can list anything that could be in a set, but there is an option that has sets having no elements. If that's the case, it's called the empty set. And there's two different ways that we express empty set, or it's also called null set sometimes. We either express it with curly brackets with nothing inside, so no elements that are listed, or we use this like 0 with a slash through it. I get like really annoyed, just a side note. One of my pet peeves is when people just do zeros like this because it means something different as a mathematician. So when people like, write numbers like 10 and then they put like the 0 with the slash in it, I'm like, that's not what that means. That means that that's the empty set. Like that's not a 0. So those do mean something different. Like having an empty set with 0 in it, 0 is an element. Okay, so like putting 0 in there is not the case. It would just have nothing, literally nothing in it. Each individual or group of objects could also be representing a subset of an original set. We use a notation, a specific notation, kind of like a C, but it's elongated. So it looks something like this. Try and make that a little bit bolder. So that tells you that it's a subset of something else. In order for something to be a subset, specifically, every element of the subset has to be in the original. And we'll do an example here in a second, but you can't have any extra elements in the subset that are not in the original set. We've done dealing with sets before. We've talked about it in graph theory a lot. We talked about like, say this is, some tree. We talked about how we list the vertices of the set. We list the edges as a set. We've done those types of things before. So in this case, we're going to list out the vertices as a set of elements. I'm going to call it V for obvious reasons, for vertices. We have 4 different vertices. They can go in any order, but I'm going to list them in alphabetical, but it doesn't really matter at all. So I'd be listing all the elements in this set separated by commas. That's important too because it tells you that this is the end of an element. So if I just listed them all as A, B, C, D, that could be representing one whole element that's called A, B, C, D. So make sure that you separate all your things with commas. In order to write a subset, for example, and I'm going to write examples because we could list them all and it would take a long time, but I'm only going to list a couple. So subsets that could be part of this set, we could take just an individual element to list as a subset or a group of elements, but the important part is that every element that's in our subset has to be in our original, but only maybe a small fraction of it. So A is an element that's in our original set, but so that would mean that this set A is a subset of that. I just pulled out like one element. Another one could be B. Another one could be D. So I could list out the original, like, individual elements, or I could list groups of elements, like AB is also a subset, or ABC. So as you can see, there's lots of different types or lots of different subsets that we could list for this 4-element combination. Notationally, if I say that, like, let's say I'm dealing with this subset AB, we would say that AB is a subset, and we use this like elongated C of our original set, A, B, C, D. But obviously we already named this set, our original set, as V, so let's call this, just so we can write it in that way, let's call this set P. I would say that P then, set P is a subset of set V. Just so you know, P subset V is not the same thing as V subset P. That would mean that all the elements in P are in V, but then, like in this case, all the vertice elements would not be in this, subset P or whatever. So just be careful with that. If I kind of do the same thing with truth tables and this kind of idea that we can have different operations and different combinations of them. So this happens with algebra, this happens with truth table values and logic, this happens also with sets. So if I combine all these elements, basically add sets together, I can combine all the elements, and this is called the union of sets. We use, obviously, again, like some sort of notation for it. We use a capital U, but again, it's not really a capital U. We use capital U for something else, but it's like this elongated type of U, and it's pretty easy to see the difference. Like, you can see that down below. It's not really a U, but it's sort of in the shape of that. It's the union of all these sets. It combines them all. And the important part here, too, there's only one thing that you have to be careful of. We don't have any repeats. So if, some element A is in both of them and I do the union, or I combine them, you wouldn't list A twice. We can also create a set that's only using what the sets have in common, and this is called an intersection. And we use like the downward U looking thing to represent that. You can kind of think about this as the and part, and this is the or, like we just did in our last logic. So let's say that we are given these three different elements, three different sets, and our first one is finding the union of them. So that would mean that in these two sets, I'm going to combine all the elements into one big set. So I have 1, 2, 3, I have 4 in both of them, but I'm only going to list it twice. I have 5 in N, and I have 7 and 8 in M. So all of the elements is a combination of everything that's in M and everything that's in N in one set. If I was doing the intersection, that would be only what they have in common. So they both don't contain 1, so I wouldn't list that. In fact, the only element that they both contain is 4. That's the only element that's in both of them, so that would be the intersection. It would only be listing one element 4. I can do that same thing for N and P. So if I do the intersection, I would list all the elements that are in both. So I see 4 and 5 that are in N, but then over here in P are 6, 7, 9, and 10. If I do the intersection between the two, there would be, I'm looking at the things that they have in common, but In this case, they actually don't have anything in common. There's not a 4 that's in both, there's not 5 that's in both, any of these elements are not in this one. So if I was going to say that they're finding the intersection, I could either list this as the empty set, or I could do, again, like that circle with a slash through it. Because this intersection contains no elements, the intersection's the empty set, these are called disjoint sets. Special word for that type of set. I forgot a letter here, so we're going to put an N here. They're asking us, is N a subset of M? Remember, that's what that symbol is. So is basically, that is asking the question, is every element that's in N in M? And I know that 4 is in both of those things, but 5 here is not. 5 is not in M. So N, we couldn't put, basically it's saying, we couldn't take this original set and then pull out a couple and put it in this other set because 5 came from nowhere. So this is not part of this original. So no, this is not a subset. Not every element that's in N is in the original set M. Like 4 is, but 5 is not. So that's the difference there of why it's not a subset. There's, again, a couple different ways that we can talk about sets. The other part is kind of transferring it into this Venn diagram way, and to do that before we actually get into representing in a Venn diagram, if we look at this combination of sets in this set theory situation, it means that like we have maybe a certain number of sets that exist in this world that we're creating. If I take all of those sets and combine them all, this would be called the universal set. And for this, we actually do use a capital U. So not a union necessarily, although it's kind of that idea. We're taking the union of everything in this situation and putting it all into one big set. If the universal set that we have is defined, then we can basically define what's called the complement, which is basically not that set. It's like the negation of it. So if I have, say, if I'm looking at a complement of a set A, the notation would be A bar. It just means everything that are in this universal set, but not in A. So for example, if I have this universal set, U defining my universal set, and I have, again, A here that's pulling out some of that universal set. By the way, all of my sets would be a subset of my universal set that are listed in this some particular situation. So A is definitely a subset of my universe. That's how I got my universal set, is I took all the elements from A and I put them in some other set. That means that there's other sets defined in this universal situation. There's some set B or something that contains 6 and 5 because those aren't part of A. So there's more things in here that we know, but for now we're just focusing on this particular set. If I'm looking for not A, basically, or A complement, that's everything that's in the universal set, but not in A. So 1 is in both of them, 2 is in both of them, 3 is only in the universal set, but not in A, 4 is in both of them, 5, again, only in the universal set and not A, and then 6 also only in the universal set and not A. So I have 3 elements that would be in the complement of A. This all should sound a little bit familiar because we've done like situations kind of like this when we talked about all these Venn diagram issues. So in dealing with kind of these universal or these intersections or these unions, we can demonstrate it visually looking at these operations in a Venn diagram way. So what I'm going to do is shade it, and I'm going to use a highlighter just because I think it's a little bit easier to see. And we're looking at all the kind of different combinations that we could do. So our first one is R union S. So that means that everything's in this particular set, which is defined as this circle. So anything that's in R is in this circle here. Anything that's in S is in this circle. And they have some overlap, meaning that they have some things in common. That's what this picture would look like. So if I'm looking at the union, it's everything in R and with everything in U. And so the representation visually would be these entire circles. So this whole section here. Basically, it's this idea of like maybe or. If I was looking at the intersection, that's anything that they have in common, which is this intersecting part in the middle where they both cross over. R complement, this is everything but R. Whatever's in R. And so our whole universal set here, I like to call it the universe because I think it makes sense in that case, but the universal set is this whole boxed area, and this universal set has things that are in R and in S, and then things that are maybe outside of that part that we haven't really clearly defined yet. But our universal set is everything that's in the universal set but not in R, which would be, like if this is R, it's everything but that. So we would shade all around R. So it would be this whole section, but not R as the circle. This is the complement of not R union S. So we already found like R union S above. It's this like whole section here. So it would be everything but that, which would actually just be all around the outside of those two sets. And then again, this kind of goes with this picture. Not R intersect S would be everything but this section. So everything but that section would be everything around that. Like that would just be the missing component of those things. So it's something like that. And the last one is the universal set. Well, the universal set is everything, so it would be the entire Venn diagram all shaded in here. That would be in my universal set. Last but not least is we're going to go back to that idea of a disjoint set. Disjoint sets, again, are things that have, are sets that have no elements in common. So in other words, and we already talked about this really, the intersection that we have, if we do like A intersect B or whatever like that, whatever, in the case of those two particular sets, and we end up getting the empty set, then that means they're disjoint. So the intersection here is the empty set. And so what that looks like, or the null set, oops. So what that looks like in a Venn diagram with disjoint sets, if there's no intersection, that means that there's no overlap here. So for example, if I know that A and B here don't have any overlap, they would be two completely separate circles in our Venn diagram. We've seen that with probability. We've seen how that looks, and so it shouldn't be too complicated. So I think it makes sense to consider that these are with like disjoint sets. It's the same idea with like a real world situation in logic.